Hi everyone, I'm presenting a paper with the title A Genetic Algorithm for the Real-World University Course Timetabling Problem. We are from the Faculty of Computing Informatics, University Malaysia Sabah. I am Selinggo. Abstract. We propose a genetic algorithm in addressing the course timetabling problem for University Malaysia Sabah-Labuan International Campus. Experiments are conducted to set the best parameter values for the algorithm to operate optimally under a computation time limit. The proposed methodology is tested on a dataset based on Semester 1, Session 2018-2019 student registration. The automated timetables are compared with the one generated manually by the admin staff of UMS-LIC. The former outperformed the latter in terms of hard and soft constraint violations, approximately 54% improvement. Introduction. There are many types of educational timetabling, namely school timetabling, university course timetabling, and examination timetabling. University course timetabling problem is NP-hard. It cannot be solved optimally by using exact methods in polynomial time. A feasible course timetable prevents clashes of courses. Effective course timetabling promotes an effective utilization of the limited educational resources, thus cutting costs for universities. Problem description. The admin staffs in UMS-LIC are facing difficulties in generating a course timetable manually. Manual timetabling is time-consuming and error-prone. Clashing of courses is rampantly reported. Addressing the problem involves assigning a set of registered courses into 35 time slots and a set of rooms. The objective is to fulfill all the hard constraints and minimize the soft constraint violations, or SCV. The hard constraints are no student can attend more than one course at the same time. The seating capacity of a room must fit the number of students of the assigned course. Only one course can be held in one room in a time slot. No lecturer can attend more than one course at the same time. Lectures can only be held on weekdays. The core curricular activity can only be held on weekend. Course that is taught by a part-time lecturer can only be assigned to the last 2 slots of a weekday. Part-time lecturers hold regular day jobs and they can only give lectures after office hours. The soft constraints are: a student should not attend a single course on a day. A student should not attend more than 2 consecutive courses. A student should not have to attend a course scheduled in the last time slot of the day. The last time slot of the day is 8 p.m. to 11 p.m. Student enrollment data from Semester 1 Session 2018-2019 is used in our experiments. The details of this dataset are given below. Related work. Most of the early approaches focus on simulating the human approach to problem solving. Graph theoretic approaches were the state-of-the-art in educational timetabling study in the early days. Techniques such as graph coloring were commonly used. In graph coloring, timetabling problems were represented as graphs. Courses were represented by the vertices of the graph, whereas course conflicts were represented by the edges of the graph. The effectiveness of meta-heuristic approaches in addressing combinatorial optimization problems has gathered the attention of researchers in recent years. Go et al. Presented a hybrid local search approach to address the benchmark UCTP instances. Chen et al. Proposed a hybridization of particle swarm optimization and local search in tackling the UCTP. A hybrid of heuristic ordering and variable neighborhood descent was proposed to address a real-world university course timetabling problem in University Malaysia Sarawak. The proposed methodology. Genetic algorithm typically comprises 6 processes as illustrated in the flowchart. Initial population. GA works on a population of individuals, updating them through the evolution process. In UCTP, the individual within the population is represented by a feasible solution. An initial population of individuals or feasible solutions is generated by utilizing the TSSP algorithm. Calculate fitness value. A fitness value determines the ability of a solution to compete with other solutions. In this work, the fitness value of a solution is determined by calculating a cost function based on SCV. In our case, the lower the SCV, the higher the fitness value of the solution. Check termination criteria. The algorithm is terminated when an optimal solution is found, or SCV is 0, or after a fixed time has elapsed. The fittest solution within the population is recorded and returned as the final solution. Selection. The selection operation identifies the fittest solutions within the population to reproduce or generate new solutions. A steady-state selection is implemented where two solutions with the highest fitness value are selected as parents. Apply appropriate genetic operators such as crossover and mutation. Crossover operator exchanges some genes between the selected parent solutions. Note that this operator is less suitable because it may induce infeasibility. A complex repair function is required subsequently to fix the infeasibility. Therefore, it is omitted in our implementation. Mutation operator involves the genes within the parent solution. The mutation operators used are transfer, attempting to transfer an event into an empty place. Swap, attempting to swap two events. Two mutation points are chosen randomly. The genes at the selected mutation points either swap or transfer, provided the feasibility of the solution is maintained. Two offspring are created through mutation on the parent solutions. Combine offspring with current population and form a new generation. The least fit solution within the population is replaced by the new fittest solution. A new generation of population is formed after the replacement. Processes B to F are repeated. Experimental results. The experiments are conducted on a laptop with an Intel i5 processor and 4 GB of RAM. By running a benchmark program, the computational time limit allowed is 42.467 seconds. A total of 31 runs were performed for each parameter setting. Figure 2 plots the algorithm's performance curves for population sizes of 5, 10, 15, and 20 respectively. Other parameter values are fixed for each setting. It appears that the population size of 15 outperformed other population sizes in terms of SCV. Figure 3 shows the algorithm's performance curves for 500, 1000, 1500, 2000, and 2500 mutations per generation. Other parameter values are held constant. For example, the population size is set to 15. Based on SCV, the best number of mutations per generation is 2000. The best and average SCV recorded in 31 runs are 1788 and 2463.94 respectively. Another selection strategy called relative selection is tested. The best and average SCV recorded are 2565 and 3226.84 respectively. It appears that steady-state selection is more effective than the relative selection. The cost timetables generated by the proposed methodologies are compared with the one manually constructed by the admin staff of UMS-LIC. The automated cost timetables fulfill all the hard constraints. Meanwhile, upon close inspection of the manual timetable, 35 students were having clashes of courses. In addition, 2 courses were assigned to incompatible rooms. The average SCV of the automated timetable is 2463.94. On the other hand, the manual course timetable recorded a SCV of 5304. Discussion. From observation, GA is indeed more computationally expensive than other single solution-based meta-heuristics. It deals with multiple candidate solutions in finding the best solution instead of a single solution as in SA. Population size is a crucial parameter that directly influences GA's performance. A larger population size gives the algorithm more exploration capability, leading to a higher chance of finding an optimal solution. However, due to time limit setting, 15 is found to be the best value for this parameter. Mutation operator helps to prevent the algorithm from converging to a local optimum. Note that GA may behave like a random surf if too many mutations are applied in each generation. In our problem setting, 2000 is found to be the best value for this parameter. Conclusion: a GA methodology is proposed to address the UCTP for UMS-LIC. TSSP was utilized to initialize a population of feasible solutions in the GA. Experiments were conducted to determine the best parameter setting for the GA to perform optimally under a time limit. The timetables generated by the proposed methodology are compared with the one manually generated in terms of hard and soft constraint variations. Our proposed methodology produced much better solutions and addressed the issues prevalent in manual cost timetabling. Future work. In future, we may test other meta-heuristics in addressing the UCTP for UMS-LIC and compare their performance with GAs. We are looking forward to incorporating a crossover operator and a repair function into GA, hoping to improve its performance. Last but not least, we may apply the proposed algorithm on different datasets of UMS-LIC to test the algorithm's consistency and robustness. The end. You may refer to the paper for more details. I am Selinggo, Faculty of Computing and Informatics, University Malaysia Sabah. Thank you and see you again.